What is DLR and why we do biped robots at the German Aerospace Center, which is mainly for space robots. Then the main part of the talk is divided in 3 parts. So the beginning will be about modeling. This is unfortunately the most equation-intensive part, so maybe not so clever right at the lunch, but after that it becomes more in which I talk about balancing and walking control. Each part will be roughly the same. So at the German Aerospace Center, the institute where I work is the Institute of Robotics and Electronics. It's located in a really small place called Oberpfaffenhofen. It's 20 kilometers to the west of Munich. And so we are integrated in the German Aerospace Center, which is a national research laboratory within the Helmholtz Association. Within the Helmholtz Association, we take care of mainly the research field of space technologies. And we have now about 29 or 30 institutes and about 6,000 researchers. And what we do mainly in the lab is of course somehow related to space robotics. We had a very important experiment for our institute, which was the Robotics experiment in '93, where it was the first time that the robot arm was used in space conditions. At that time, the robot arm was inside of the space shuttle, and it was teleoperated from space. So you have to copy this very huge time delay, and the robot basically autonomously or semi-autonomously was able to catch free floating objects. At that time, we realized that for space applications, we need different type of robots than this kind of industrial systems. At that time, we started the development of lightweight systems, where we have all electronics and all sensors which we need to control the robot integrated into the structure. This led us the 2 generations of lightweight arms to the development of the lightweight arm 3, which is now a commercial version, so it can be bought already from the company. And we also retested the same technology which was used here, again on the International Space Station, but now at the outside part. And it was tested here again in teleoperation experiments, but now we didn't use so much predictive simulations, but we used more control methods like wave variables or nonlinear control for controlling the system independently. One of the unique features of these robots is the tight integration of joint torque sensing, which was already done in the very early days and refined in the more newer versions. And in the control approaches developed for these robots, we always try to combine basically robustness in the control with performance. And for the performance, we have the inner loop joint torque feedback, which basically makes the system highly backdrivable and very sensitive, very variable. And we combine this inner loop torque feedback with an outer passivity-based controller, which led to very robust behaviors, which you can see here. So you can see just in robot manipulating some balls or manipulating small objects, and during that time it's always compliant control. So humans can interact with the robot because everything is based on a very sensitive joint torque sensor. That was the situation up to, I would say, 2009, that we had a robot manipulator, a 2-arm manipulator system, for which we developed a variety of control approaches, mainly based on joint torque sensing. And at that time, 2009, we thought about how to extend this system into more humanoid levels, humanoid forms, more human-like systems. And basically, we started 2 developments. One was the development of an anthropomorphic hand-arm system, where we have compliant elements integrated into the joints. So here, the joints itself are elastic and are able to catch impacts. And this type of actuation thing is more human-like, and that will allow you, on the one hand side, reach higher performance, but also implement very robust behavior when we have impact system. And the other development about which I will talk in the following is the extension into more human shape. So we wanted to test the same compliance control which we had for the adjusting robot, also on the leg basis. And for that, we first decided to use exactly the drive technology of the lightweight arm and assemble a biped system based on it. And this was done in 2010, mainly by a student project, where we took really the technology of the lightweight arm and redesigned some new structures, but left the drive units as compact units as they were. That allowed us to have right from the beginning position control and joint torque control in the systems. So we can always compare position-based approaches with torque-based approaches. This is also something I will explain later during the talk. We decided for a rather small foot shape of less than 10 centimeters in width, which we decided for mainly two reasons. On one hand, it allows more dynamic walking, where the COM moves further outside of the support corridor, and also it's possible to step over obstacles more easily or on stairs more easily, while if you have a very large feet, this can be more difficult because you need to make quite large steps. And so this was the situation in the beginning, when we had a biped system with joint torque sensing and position sensing. And after 2 years of research, we decided to go a bit further, because with this system we could study all kinds of walking algorithms. But in the future, we also want to extend more towards multi-contact interactions. That's why we decided to redesign the hip part and put an upper body on the system. And this is what led us basically to what we call now Toro robot, which was finished just in the beginning of this year, and where we again had joint torque sensing in all the joints. Also, the upper body is built based on the technology of the lightweight. The head is still a bit dummy head, so it doesn't have much sensors, but we hope to update this until the end of the year. So this shows the technology which we have. And before starting with the more mathematical part of the talk, I want to show just as a beginning the very first walking controller we had. So this was really at the first automatic affair right after building the robot. It was, I think, 2 or 3 weeks after the robot was finished, we had to show it on the fair, and we implemented basically I would call it a classic approach, which uses a 7P-based balancer and a pre-fusion scheme for the walk generation. So this was the very first walking gait which we implemented on the robot. And the following I will also come to the approaches which we now use based on capture point, more at the end of the talk. Okay, but let's start. Okay, before one more video, I forgot about this. So this is the system like it's now. You see it in 2 different applications. One is just a manipulation task where the robot goes to the ball, which it detects via a Kinect sensor and manipulates it. And on the right-hand side, you see a very first multi-contact application where the robot is leaning some part of the body weight onto the arms. So here it has to distribute the forces between the whole system. The arms are compliant controlled, the ankle is very compliant, and along the body it's a more stiff behavior in order to keep the body shape. And here this robot is carrying a ball of 3 or now we use 5 kilos, which is still possible for this robot. So I think one could extend up to loads of 10 kilograms, but this is the range which we can implement with this robot. If the loads are higher, then at some point the structure will be okay, so this shows the systems which we have. Now I would like to come more to the mathematical part of the talk and explain what type of modeling approaches we use and how we control the robot during balancing and during walking. Okay, let's start with modeling. When we look at the modeling of the bipedal system, it's clear that we have to start with studying multi-body dynamics. And here we can distinguish between kind of complete models and more simplified models. So the most complete description of the bipedal robot really would be a floating-based model, where the interaction forces between the feet and the ground would, during single and double support, give us additional constraints, which then can lead to fixed-base models, which are dedicated to specific contact situations. So So we can either deal with this kind of complex models, or what is often done in walking and running is that we look at more conceptual models, often called template models, where for different gait types, one uses different models. So for walking, one very common model is this car paper model, while for running, I'm sure you heard everything about this little model already yesterday by the talk of Morris Mouse. So I will skip totally the split model because I think it's not now. Okay, I will focus more on this type of models, either complete models or simple models for all. And if we look once more at the comparison between floating-based models and fixed-based models, it's clear the basic components which we need to model such systems are the Lagrangian dynamics. Then we have constraints due to the contact forces, and we have transition equations. And we have, whenever we have an impact between two twisted parts. And in a free-floating model, we would basically cope with all these components individually. While if we decide to compute a fixed-based model, and we have to do for each of these different contact states, we have to compute a different fixed-based model in which we either have a single support constraint, a double support constraint, or other more complicated constraints like this. And in all these cases, what really makes the difficulty for walking control is that if we consider such either free-floating or fixed-based model, that we always have constraints on the ground reaction force, which we have to fulfill during the walking control. So this is true for both fixed models and free-floating models. Okay, now let's look more closely at this type of multi-body systems. If we look first about the very general description, what is the configuration space of the system? Configuration space, of course, the robot itself has its joint angles, so we have a set of Q of joint angles. And in addition to that, in order to describe the full state of the system, at least for the floating-based model, we have some coordinates for one base state in the system. And these coordinates for the base basically give us 3 position and 3 orientation variables. So our configuration space clearly is bigger than just the joint space. It's basically the joint space plus those 3 coordinates for the floating base. Okay. Now, this is just the configuration space. Let's look more closely about how the dynamics looks and what structure the dynamics will be. If we compare first with the standard manipulator, the fixed base manipulator, then we again have the joint angles, some joint torques in each joint, and we assume now that the robot is interacting with the environment at some specified point here at the tip of the robot, here this external force. Then a classical Lagrangian modeling approach would lead us to a multi-body dynamics like this, with mass matrix, centrifugal terms, gravity terms, the torques, and the external forces mapped with the Jacobian transposed onto the multi-body dynamics. So the classical Lagrangian dynamics we can derive. However, for a bipedal robot, this is clearly not enough because it's a fixed-base system, and what we want to have is a system where the system can move its contact points from one contact to the next. So we need to describe the contact points via additional variables. And if you do this, then of course, in addition to these additional variables, we also have a respective force acting on the free body. This leads us to a more complex dynamics of now a free-floating robot, where we have, as the state, x, p, and q, and we have just an extended inertia matrix. And on the right-hand side, we see that the joint torques only act at a part of the system, while the other forces, like external forces at the tip or external forces at the main body, act also onto the first 3 equations. Okay, this is just one single serial robot in floating base. If we extend it to a bipedal case, then the only thing which is different is that we have now two external contact forces. So at the right-hand side, we have again the torques acting at the joint space, and we have external forces at the right and at the left. Here the different Jacobian matrices, they map into the Lagrangian multibody dynamics. Okay, if you look at these dynamics equations, it looks first of all very complicated. And for different purposes, it makes sense to somehow transform this model into different shapes. And and I will basically show two different versions or different formulations of this dynamics, which will be used either for balancing, or the first step we do, okay, for that we see it's mentioned already, it's an underactuated dynamics, and we have the lateral constraints described in the picture. Okay, for transforming the system in a more intuitive form, one very common approach, which is actually well known in space robotics, is to use not the coordinates for the base as system coordinates, but use instead of the position variables in xp, we use the position variables of the center of mass. So xp basically is mapped in the position of the center of mass and still the orientation of the. And if we do this, our full multibody dynamics becomes a very unique form. Because we see in these modified equations, where we have now the coordinate c and the joints and the orientation of the body, we see that in this inertia matrix, we have a decoupling between the multibody effects and the effects on the center of mass. Same for the gravity, and we see that the only coupling between those two equations, the first equations for C and the equations for Q, only coupling happens in fact via the contact forces. And this is a very intuitive shape of the dynamics, because when we extract only the first three equations, what we can obtain again is the conservation of momentum out of these equations. So even we started with a very complicated dynamics which contain the all multibody effects. We see that the conservation of momentum corresponds to what we know, let's say, from physics, for the center of mass dynamics, for any multibody system. So the acceleration of the center of mass is governed by the gravity terms and all external forces acting on the system. And so this is a very nice shape which we can use in the code. This is not the only thing one can see from those equations. It's very direct and visible, but what is not so direct and visible is that the next three equations would correspond to the conservation of angular momentum. So what we have for the position variables for this conservation of momentum, we have a similar property also for the angular momentum. So we can extract from those complicated multibody dynamics still the conservation of angular momentum, meaning that the change of the angular momentum is the sum of all external moments. One moment is generated via the gravity force, and other torques are generated via external torques interacting somewhere onto the body. So from this complicated multibody dynamics, we have let's say, derived very common properties known from physics. And now the next step would be to also combine those two equations in the following form. If we look at the system from this world fixed coordinate system, and the torques acting here are the torques in the world fixed coordinate system. If we express this torque by a pair of force and torque at any contact point between the foot and the ground, Fp and tau p, then we know between this torque and those force and torque, we have such a simple relation. And with this simple relation, we can combine those two equations, basically by putting the forces into here, and then putting the whole equation into here. We get a condition or an expression for the torque acting at a certain contact point tau. And this expression for the torque is depending on the total angular momentum of the system and on the remaining terms. And basically, this is another equation which we will use in the following, mainly for deriving simplified models out of the dynamics. So this equation as it is here is not simplified at all. So this is a general expression for the torque acting as a given contact point between the two compounds. There is no whatsoever simplifications. And those two equations will be the basis of all the controller designs which I will talk about. So either the multi-body dynamics in which we have the CM as a system coordinate, or an expression for the torque at the contact point between the foot and the ground. Okay. And with this, I would come now to a set of simplified models. And in order to make the transition to the simplified models, I would like to discuss the concept of the zero moment point, which I probably see most of you working in software robotics know already, but I just, as a quick reminder, I would just go over these slides. So the zero moment point is a ground reference point, which basically describes us how the ground reaction force is distributed. If we look at this simple case of a one-dimensional situation where we have between the foot and the ground a given pressure distribution rho. And if we look at how pressure is distributed, it's very intuitive, very clear that the pressure distribution will only be a positive pressure because basically the ground cannot pull on it. And if we compute out of this pressure distribution the total force and moment at any given point, we basically get one force and one torque. At any given point, it is a positive torque. And the zero moment point is now defined basically as the point where the torque becomes exactly to zero. So if we search at contact between the foot and the ground, the point where we can express the whole pressure distribution by only one force with zero torque, then this point is defined as the zero moment. And from the fact that the way this is designed here in 1D can of course be generalized very easily to a pressure distribution in 2D for giving us the location of the second P in 2D for linear time. And it's also very intuitive, I think, that the second P will always lie in the convex hull of the support polygon because the pressure distribution is only given positive force. Okay. What can we see directly from the very definition of the ZP? We see that the ZP can never leave the support polygon. One also has to say that it's cannot be used as a stability criterion, even if the ZP is is inside of the support polygon. It doesn't mean that the robot will fall. It just means that the foot will not tilt around its edge. What happens to the rest of the system is not said at all about by the ZP. And it should be mentioned, it tells us nothing about sliding, and it's defined in its original definition only for flat contacts, for flat substrate. And on this slide, we see a very rather old picture where we see how in the early days the ZMP was used for controlling robots. Basically, this is a robot from City University, and they basically had predefined foot trajectories, so they didn't modify the trajectory for the foot or for the hip. They just replayed that and tried to control this counter mass at the top in such a way that the ZMP would keep inside of the support polygon in order to make sure that the foot would not start tilting. This was one of the very first ideas of how ZMP can be used for controlling robots. Okay, having defined the ZMP, we should think about how can we relate the ZMP to measurable quantities in the robot. And we can think of either compute the ZMP via measurements or drug sensors, or we can compute it from measurements of the dynamics, basically position and velocity trajectories. if we try to use a force torque sensor in the foot for measuring the interaction force between the foot and the ground, then we can derive the equations for the ZMB from the very definition of the ZMB. So if we map basically the torque and force measured by the sensor onto any point in the ground surface, we basically get the torque expression like this. It's just torque plus lever arm times the force. Now if we solve this equation for the ZMB such that this torque is exactly zero, we get the equations for the ZMB. So very straightforward from the very definition of the ZMB, we can compute based on the measured force and measured torque in the ankle, we can compute the value of the second theory. Okay, this is one version which allows us to measure the ZMB. However, for control approaches, we want to have a model of how the ZMB is related to the dynamics of the system. And for that, one common approach is to look again at the multi-body dynamics, exactly as we had it before, where we express the torque in the body coordinate system by a force and torque at the foot contact. And we had it before already. We have a mapping between these values at the contact point to the world coordinate system. So just the lever arm times the force plus the torque. And if we utilize this, then we can again formulate the conservation of the total momentum and total angular momentum, and utilize this equation in order to combine two equations, in order to combine to compute an expression for the torque at the given contact point between the foot and the ground. And as I mentioned before, so this is exactly the same equation as we had before on the multiple slide. The total angular momentum and the total momentum are not at all simplified. And if we set here the horizontal torques around the x and y axis to 0 and solve this equation for point B, then the expression we get is exactly the 0 momentum, and without any simplification of the system. So it depends on the total angular momentum and on the total momentum at x and z. Okay. And starting from this very definition of the ZMB, we would now go towards more simplified models of the problem. And one way of deriving a simplified model is to think about the mass concentrated model. In this case, the total momentum would be just the mass times the velocity of the CM, and the total angular momentum will be the lever arm times the momentum. And if we compute here these expressions for the momentum and angular momentum, we put them into the original definition of the ZMB, then we get these simplified equations. We see that if P and L all depend on M, the expressions all become independent on the total mass, and we just have basically the CM location here, X, and we also have a term depending on the vertical motion. This is still a coupled nonlinear equation, and what is often done then is that this, so this is already a simplified dynamics because it considers a mass concentrated model. But this is often even more simplified by considering the case what happens when the CM only moves in the horizontal. So if the CM doesn't have any vertical component. If we do this, basically those two terms cancel out, and we get now a linear dynamics between the ZMB location and the motion of this element. And the equation that is written here is often called the car-table model. So I think Kashida was referred to this term for it. And in the car-table model, we have this linear second-order dynamics. And the idea here is to consider the motion of this CM and its effect onto the ZMB. So if we know how the CM moves, we can exactly compute the trajectory for the CM. This very simplified model is in comparison with another simplified model, which is called the linear inverted pendulum model, which is formulated here. As you see, the equations are exactly the same. They are also derived stating they are the same arguments, but the interpretation is a bit different between the Carr-Table model and this linear inverted pendulum model. While in the Carr-Table model, as I mentioned, we consider the motion of the CUM as the input, and we get the ZMP as the output, depending on how the CUM moves. In the linear inverted pendulum model, the causality is different. So here we consider it more or less like a proper differential equation, where we have the ZMP as an input, and we get the dynamics. Via the dynamics, we get the motion of the CUM as the output. So this is often a bit unclear how the two models, the linear inverted pendulum and the Carr-Table model, are related to each other. Okay, so this gives us basically two versions of very simplified dynamics, which later again are used for the there is one more thing which we can derive based on this dynamics, which is the so-called capture point, which is also a very fundamental quantity in walking control, which more and more people use nowadays for deriving their control. While the ZMP was really an expression or an abstract view on the ground interaction force, the capture point is defined a little bit different. And for the capture point, actually, when you look at the literature, you find some other quantities which have different names, but are exactly the same as the capture point. One is the so-called extrapolated center of mass, which is the name which was proposed by Bonn. And the other one, the divergent component of motion. This is the quantity which is used by Honda, is also corresponding to this capture point. So you see that many people nowadays have used the capture point in one way or the other. And let's look at what is the definition of this capture point. The capture point is defined as another ground reference point, similar as the ZMP, but it's not directly related to the interaction force between the ground and the foot, but it's related to the motion of the system. In such a way that we say the capture point is the point where the robot would have to step in order to bring the robot to a stand. This is a bit simplified, this definition, because what does it mean, point where to step? So this definition comes from the consideration of the point foot. So in other words, we mean by the capture point the point where we have to put our ZMP and keep it there in order to bring the total motion of the system to a stop. And it will stop right on top of the capture point. And from this very definition, at least for some simplified models, one can derive an exact expression for the capture point. So two examples are the linear inverted pendulum, which I will discuss here. But also if you have another model like the inverted pendulum, so not a linear one where the CUM is kept to the constant height, but the normal inverted pendulum model also allows to include a capture point. But if we keep talking here about the linear inverted pendulum model, then we have this kind of dynamics. And it's a linear dynamics in which we consider the ZMP as the input and the motion of the CM as the output. And since the system is so simple, it's a second-order linear system, we can directly write the solution of the system for a given constant ZMP. And the solution is basically given here, but it's superbolicus and sinus-superbolicus terms. So starting from any position x0 and velocity x0 dot, and keeping the ZMP at a constant point, we can compute, we are solving this linear dynamics, the trajectory for this linear. And if we now require that the motion comes to a stop, it means from the dynamics we clearly know that the motion can only stop right on top of the ZMP. Right? If we now require that asymptotically the CUM approaches the constant ZMP, then this point, which we derive here, will be have the meaning of the capture point. So if we put in the p here on this side, it basically cancels out here and here, and we can exactly compute the capture point as a function of the current system state and system velocity. And the solution is very, very simple. It's given here. So the capture point is nothing else than a combination between a position, the CUM position, and the CUM velocity, divided by this omega, which is the height frequency. And now, if you consider this system, it was consider this variable. It was derived from the definition of a point value step, but it has such a form which has more advantages if we use it in a different way for control. Because if we use the capture point not as a point value stop, but as a system variable, then the dynamics will simplify quite a lot. This is shown here. So if we go away from the CUM and CUM velocity to the CUM and the capture point, the system variables, it's just a simple system coordinate transformation. Coordinate transformation is here. Then the second order dynamics gets basically this form. So the first equation is nothing else than the definition of the capture point, and the second equation shows us how the capture point is affected by the second field. So, and if you look at these equations carefully, you see that these are basically decoupled equations, which are only coupled via the second via the capture point. So we have a cascaded dynamics with, in the first equation, a stable dynamics for the CUM and an unstable dynamics for the capture point. And this separation into stable and unstable dynamics, of course, has many advantages for both for planning and for control, which I will explain. And yeah, one comment I would like to make about this type of variables. It's a capture point. Here it's not used as a point variable step, but it's used as a system variable. And it's a combined variable between position and velocity. And such combined variables are actually very well known in adaptive control. So if you know the adaptive control of lean and lean, it also has a combination between a position error and a velocity error. And it uses this variable in the design of the nonlinear tracking control. And the same ideas, how to simplify the dynamics, also apply here, because it separates the dynamics from the second order into the first order. Okay, now we've talked a lot about the capture point. Of course, you can ask the question, how does the capture point is really relevant if you do not want to consider stopping the robot by one step, but if you want to consider walking. And in this picture, you see now a comparison between the simple linear embodied pendulum model and some measured data from measured human data. And what you see, this X is basically the second P. The strong line is the CUM, and the light line is the capture point. And what we derive now from the simple linear system is that the capture point should go basically on lines between starting always from the second P. The capture point should move along lines. And if you look now at human data, where again we have the CUM trajectory, the second P is given here at by the X, then of course they are not only the lines, because in the human motion there is not only the single support but also the double support phase, where we basically shift the CUM from one point to the other. But in between you still see this linear behavior. Only basically instead of having the sharp edge or letting the second P jump from one point to the other point, we see a smoother motion where the second P basically moves gradually from one point to the next, meaning also that the capture point moves more quickly. But we can see the same trend also in human data. Okay. So this is one quantity which we will use later for the moment. The last quantity I want to talk about is the so-called centroidal moment pivot, because it's somewhat related to the balancing, which I discussed next. And the centroidal moment pivot is another ground reference point, so we have already two, right? We have the second T, which gives us a point corresponding to the contact force. We have the capture point, which is the point where we step in order to stop the robot. Now, yet we have another ground reference point, and it's called CMP. It's very hard to distinguish between the ZMP and the CMP, especially if you are an American speaker. Then, anyway, this centroidal moment pivot comes from this, is motivated by this. If we observe, again, human motion data, then one can see that the total angular momentum of the system around the CM, it's not exactly zero, but it's kept small during the gait cycle. And the centroidal moment pivot was now introduced as a point in order to express how much the angular momentum, or how much effect the angular momentum has now. And let's explain its relation to the 7B's to explain it. If we first look at the simple linear inverted pendulum, we have as forces only the gravity force, the acceleration force, and the ground interaction force. And if we compute based on force balance equations in dynamics, we get again what we had derived before, the simple linear inverted pendulum dynamics. However, if we have not only these forces, but if we also have a torque acting on the system, then in order to counterbalance both the torque and the forces, then the ground reference force has to move basically away from this point directly under the CM. And the difference between this point under the CM and the real ZP is basically gives us how far the CMP is away from the ZP. And if we again compute the full dynamics by making the force balance equations, we get a dynamics like this. And this dynamics we will look again when we consider the balancing. So here we have the linear inverted pendulum dynamics, also a vertical motion of the CM, and we have an effect of the torque acting on the system. Okay, so what we've seen for the CMP, it basically corresponds to how much angular momentum plays a role in our work. And what is obvious is that by the 7B cannot lead to support polygon such as C, because it does not apply for the C. And so now we have discussed various ground reference points and various points. And in the next part of the talk, I would love to see how we can utilize these ideas in order to design controller, both for balancing and for motion control. And let's start about the balancing. If we look at human balancing program, balancing is basically solved by utilizing several different sensor modalities. We have the vision system for looking where how the environment is located with respect to our main reference frame. We have a vestibular system giving us information about the head acceleration and head orientation. And we have a somatosensory system giving us information about which forces and which kinematics is involved in the postural situation. If you now look at the robot, it's actually not so far away. We have basically the same kind of sensor modalities. We can have a vision system, okay, this robot has a dummy head, but it could have a camera. The IMU is a very common sensor. Joint position sensing and force sensing in the feet is also very common. What is not so common is joint torque sensing. Joint torque sensors can be understood here as an additional sensor modality also related to this somatosensory system. Okay. And these are the sensor modalities which can be used for balancing. Now, let's look at the human. What different strategies can we observe when we have a human standing on a platform and perform different pushes of different lengths? Then what one can observe is that for very small pushes, the human basically follows an angle strategy. An angle strategy means that it only tries to produce torque at the ankle in order to balance the total posture on top of its support. If the push is bigger, then the human would also start to use the hip in order to mainly introduce some additional angular momentum, which can be used for only for larger pushes stepping. Now, if you look at the robotic counterpart, what we can identify as an anchor strategy is basically can be found in ideas like force control or ZMP control in the control structure, while the hip strategy can be somewhat identified in approaches on angular momentum control. Okay, what is formulated here just intuitively, we can also see by looking a bit more into details of the equations. We have here this, again, a force balance situation that we have gravity forces, acceleration forces, and torques acting on the system. And the total dynamics is basically given like this. And previously, the inverted pendulum dynamics, we used only the ZMP as an input, which basically corresponds to an anchor strategy. We use only the ZMP for controlling the motion of the system. But in addition, we can use the total torque around the CUM, so the total angular momentum, for also influencing the motion of the CUM. This would correspond here to a hip strategy. Okay. So these were just some basic ideas and definitions about balancing. Now I would like to come to one very classic approach, how balancing is implemented in many position-based bipedal robots, based balancing strategy based on the system. And the idea is always, if we want to implement balancing, we always want to have a kind of compliant behavior. Because if we would have a completely stiff behavior, we could just increase the external force, and when the contact force moves until the edge, then the system would start to tilt around the edge with contact force. However, if we have a fully compliant system, then if you push the robot from the side, if it's fully compliant, the total ground reference force or contact force can stay in the middle of the foot, but the whole posture of the system may come to a very difficult situation where it's hard to recover. This also shows very intuitively that the ZMP is not the stability criterion whatsoever. And in most cases, we want a somewhat compliant behavior, where when we push the robot from the side, the robot reacts not completely stiff, but also not completely compliant. So in a controlled, compliant way. And one very widely used, I think, approach, which was published several years ago by Joy, a group from KISS, is shown here. The idea is to have a position control robot with joint position control and inverse kinematics. And we can command to this position control robot the desired velocity of the CUM. Now, how can we use this desired velocity in order to balance the system against external forces? We have again this force balance situation where gravity force, acceleration forces, and ground and vector force are acting. And in addition, we have an external force, which acts in the same way as the acceleration force. And Joy proposed now a stabilizing algorithm in which, for the desired velocity of the CUM, one doesn't only have a feedback term which lets the CUM follow a given reference trajectory, but he added a second term in which the ZMP is used in the feedback. And the second term is used here as negative feedback gait. And if you consider this situation, that it means if a force is acting from outside, it would basically produce via this feedback term a positive acceleration on the CUM, and the second term would basically limit how far the motion goes away from the equilibrium. And if you're more interested in what exactly would be the equilibrium point from such a situation, you can take the dynamic equation and the controller and compute also effective stiffness from this. So one can really assign a given desired stiffness as a reaction to external forces and parameterize such a simple controller system. And there's also a stability condition which is, so it's on the stiffness it's very easy to see that Kx must be bigger than Kb in order to have this positive stiffness. And this additional requirement about the omega comes from this analysis which also considers absolute stability, not only normal values. Okay, now let's look at a typical situation where such a position-based balancer is applied to our model. We have, so we extended the control a bit, having not only compliance in the horizontal direction, but also in the vertical direction. This is position-based balancing. You can see that for any external forces acting here on the main part of the robot, the behavior is balancing quite nicely compliant. Okay, so this is one version, which was, as I mentioned, a position-based balancer. This is a very standard approach, so it's standard in the horizontal direction. The extension to orientation and vertical motion is not so standard, maybe. Now let's compare this with a torque-based balancing approach. And the torque-based balancing approach follows a bit a different strategy. Here, if we look only about forces, if we have an external force acting onto our system, what we basically want to do in order to balance the Cm over the support polygon is that we want to have a reaction force acting at the Cu. And this reaction force can, on one hand, compensate for gravity and implement the compliant behavior of the PD-like controller, as it's shown. Okay, what is shown here for the positions by controlling the Cm. We can extend it also for the orientation with the PD-like controller for the orientation, corresponding to the orientation. And those two quantities, the desired force and the desired torque, give us a desired range. A combination of force and torque acting at the Cu. Now the question is, having such a desired force acting at the Cu, how can we implement this on our own? For implementing this, we basically have to first distribute this desired range onto the contact points between the foot and the ground, because the foot-ground contact is the only way how to put external forces onto the system. So we have to realize this range onto Cm via contact forces between on the right and left. And when we have the contact forces, we still have to map or implement these contact forces via joint force. How that works is shown for the few slides. So the idea, the first idea is the question how to distribute contact forces from the Cm onto the feet. And what you see on this slide is that this is a very common problem in robot grasping. In robot grasping, a hand would basically try to exert given desired contact forces onto the object in order to achieve a net range onto the object. And what is true here for the object is also true here for our balancing situation, only with inverted dual roles of the environment. Okay, let's look one slide at how force distribution is solved in robot grasping. Robot grasping, basically, people look at the mapping between the contact forces Fc via a grasp map onto the total range of the system. And this grasp map consists only basically of kinematic mappings. These kinematic mappings depend only on the position and orientation of the contact. And then it's a very common problem in robot grasping to find a set of contact forces which are on the one hand side fulfilling all conditions on the friction cone and unilaterality conditions in such a way that the desired net range, so the total range, is achieved on the object. And the same solution we also copy basically for this application in balancing. And here, the contact forces basically correspond to position forces on the feet of the robot, and the thrust matrix corresponds to the kinematic mapping from the contact point to the center of the system, showing the rotation matrix and the electron. Okay, so this is the equation we want to solve. We have a given desired range on the object, or on the CM, given from a balancing controller, and we want to realize some contact forces. We want to compute contact forces which realize this desired range. And one way of solving this, as is often done in grasping, is to formulate the whole program as an optimization problem. In this case, a constraint optimization problem, because we have friction constraints and these unilaterality constraints, meaning that the contact forces should be only positive. And in this optimization problem, we basically have three terms. The first term is highest priority, corresponds to the force we exert on the CUM. The second term corresponds to a torque, which we exert around the CUM. And the third term is just a regularization term, which means that if I don't need all contact forces FC, they're not needed null space basically, or all not necessary contact forces should be as small as possible. So it's just a regularization. Okay. And this problem is then basically solved by a quadratic programming solver, giving us a set of contact forces at the feet. With the contact forces at the feet, we still have to map them onto the joint rods. And for considering the mapping between the contact forces at the feet to the joint rods, we would look now at the full multi-body dynamics. And as mentioned in the first part of the talk, if we use the CM as a system coordinate, then we have a decoupled CM dynamics here, which is only coupled to the multi-body dynamics via the contact forces Fi. The rest is different. And via this Jacobian, we see how the contact forces, which are forces acting on the CM, are coupled to the multi-body dynamics. And then basically one could derive different controllers, either inverse dynamics controllers, or what we implemented here was a Jacobian transposed controller. So it's basically a possibility-based approach which implements the contact forces, we're just mapping them from the contact points onto the joint rods. And the behavior you see on this slide. So here my colleague is first only pushing the robot at different positions, and at the top you see again the whole control flow. We compute the desired range on the CUM. This range is distributed to the contact points and then mapped into the joint torques. The local controller is just a joint torque control, not a position. Okay, the video you've seen here was fairly similar actually to the position-based approach. The next video shows a more challenging task where the robot is now standing on a movable platform, and here we also integrated review information. Since the only task of the robot is basically to push with the forces down, the system becomes very robust with respect to uncertainties in the foot ground. And this kind of robustness with respect to uncertainty in foot ground contact is also shown in this set of experiments, where we put the robot on a test bed, where it's actually a test bed for measurement of human cushions. So there are two platforms which can move vertically. And there's also a force sensor. Normally a human is standing on this platform, and the actuators are performing a perturbation of different oscillation frequencies. And via the force sensors we can then measure the reaction forces. And in a human, people try here to identify which stiffness the human uses in the joints or in the legs in order to perform different balancing motions. It's a setup from our bionics. And we put basically the robot on the same system, and use the system just for evaluating the performance of this torque-based balancing. You see, even now we have disturbances or uncertainties in the contact points between the foot and the ground. The system still can perform the balance. This would be the main advantage here against the position-based controller is, I would say, that the torque-based solution has a much higher control rate on the force level than the position-based. Okay, so we have seen two different balancing controllers, and I would like to show a little bit more into the comparison of the two systems. The first video shows just a simple impact experiment, and I only show it here for the position-based controller. For the torque-based controller, actually the behavior would not be so different, at least what you can see from the video. If you look at the signals, it's behavior is good. Just from the video, it's similar. So we can see here the nominal balancing task is basically possible with those approaches. The next video shows whole body interactions. This is more interesting because now you see when the human touches in the position-based solution at different positions, then the behavior is quite unintuitive. Because in the position-based solution, we use the measurement of the force in the foot in order to mimic the compliant behavior for the main body. And if our force is exerted far away from the main body, we have a huge lever arm to be considered. On the other hand, in the torque-based controller, this doesn't happen because the torque-based controller is independent of an additional reference frame. So in that way, of course, you can change the reference frame in the position-based controller in order to make the interaction fit better for touches at the level of the feet, but it will then again feel funny for touches at the interaction forces at the top. So here in the position-based controller, you always have to choose a reference frame, which is not the case for the torque-based. And the last comparison considers similar configurations. So in the position-based solution, here we use the standard inverse kinematics, which would basically stop when the robot is moved in the full inverse singularity. In the torque-based controller, since there is no inverse kinematics used and only a Jacobian transpose mapping, the system becomes also very robust in similar configurations. So these are basically the advantages of the torque-based solutions. There is no singularity, and the control is completely independent of any reference. But I wanted to say that on flat floor, both approaches actually work. Okay, so far we have seen balancing based on either position and torque control. Now the balancing controllers, I would say, form the basis of different types of walking control. In the case of the walking control, I would again discuss two different versions. One is a more classical version. It's the preview control proposed by Cachedro. And the second one is a feedback controller utilizing the Cachedro. Again, I would like to show both approaches and compare the two. And you will see that both of these approaches are compatible with different balancing controls. First of all, if we look at classically walking controller based on conceptual models, the conventional structure is like this. We have an algorithm for footstep generation, which is discrete information. Then this discrete information is then transformed into continuous trajectories for this CUM and the second B by means of a pattern generator. And the one which I discussed today is this idea of preview controller, which was proposed by Kachina. And on Thursday, Viva will show you many approaches based on different versions of model predictive control. So this basically would be the link to this lecture. In any case, whenever you use a pattern generator, giving desired trajectories for the CM and 7P, when you use the open loop, only based on the self-concept, you need an underlying stabilizer which basically does the balance. And one typical example, as I mentioned before, is this balancer by Joy, which can be used with fairly old, command language generators. Okay, so for walking control, I would like to look again at the simplified model description. We had discussed the linear inverted pendulum and this card table model. In the following, I will start with the card table model for this first approach, so this preview control, while the second approach will be based on the linear inverted pendulum. Okay, the card table model, our input is basically the motion of the COM, and our output is the setting P of the system. In order to allow this from this dynamics, basically Bachelor proposed to extend the system into a third order dynamics by considering not the acceleration here as the input, but considering the jerk of the COM as an input. If you do that, then from the COM and COM acceleration, which is then a state in the system, you can get the output of such a simple linear continuous function. So here the input is not the acceleration, but it's the jerk in the system. So it increases the order of the system. And the first step here would be basically to discretize this model in order to get a discretized full order. This can be done in a fairly straightforward. Then the idea which Kachida proposed for generating a walking pattern was to adopt what is called the LQR preview control, known from automatic control. And here the idea is not only to design a simple feedback controller for the dynamics, but to augment this feedback controller by a preview action. So by the idea is if you know basically that you will make a right step or left step next, you know already in the current instant that 1 second later you want to move your second E from the left to the right. Since if you plan 1 or 2 steps ahead, you always know some reference motion in the future. And you can use the future reference motion in the design of the controller. And this idea was formulated in the sense of a LQR controller by those authors from a very intuitive example which Kachida always uses is basically this situation when you drive a car and you use a classical feedback controller. It's basically like driving the car while moving it only through the back mirror. Because you only look at the current error, how far your car is away from the border of the controller. But if you look ahead, basically you have previewed reference controller. You know that not only how the current state of the car is, but also how your desired trajectory will be. Then you can start to steer already before you know there's a control tower. This is the idea of the preview. And the effect is basically that we don't have a step response like this, where only when a control error happens, basically this control system starts to react. But even before the reference trajectory jumps to a different position, the control system can already start to act. So it's basically acting instead of reacting. Okay, now let's look at the theory behind this type of LQR preview control, which tells us how can we introduce predictive information in a feedback control. If we have a linear time discrete system like this, the system matrix A, and input vector E, and output vector C. Then we, of course, make a few assumptions on the system. First of all, that it's stabilizable and detectable. And then there is one additional assumption given here. And this assumption is something I will mention in 1 or 2 slides later. Now let's take it just as a mathematical addition. We assume now that we want to control the system in such a way that we know for value of any future time steps, the reference trajectory. And for the controller, we want to apply an LQR controller with the cost function like this. The cost function has one term in the control error. So it's an infinite cost function, infinite control horizon cost function. There's the first term corresponds to control error. The second term corresponds to the state error, but not the direct state error, but the differences in the state error. And the third term uses a cost on the control input U, but also on the differential control input. And this is the idea of using the differences here, not the original state and original control input, comes from the fact that by using the differences, we automatically will get an integral action to the control. So this is doing it, I think, the control output, and having differences instead of the state is leading to an integral action. Okay, now the system is written in the state x and output y, while the cost function is giving me the differences in x and y. So the first thing we have to do is to make a coordinate transformation from the state x to the delta x, and from u to delta u. And what we can see by only computing the delta of the first equation, we basically see that the system dynamics for the state is the same basically for the differential step. We're just taking basically not k plus one step, but a k step, and subtracting the whole equation from this, we basically get the same equation by with the delta steps. And if we compute also the control error, nothing else than the difference between the output minus the reference. And if we compute the state the dynamics for the control error, we basically get the first equation. The first equation, we see it not only depends on the last control error, but it also depends on the future references in the system. So I think I go a bit faster over these derivations because the concept is simple, but the following the example equations is maybe a bit hard and short time. Anyway, you can make these coordinate transformations from x and u to delta x and delta u. Get basically these extended system equations where also the future reference is included. And in order to not only have the future reference for one time step, so this future reference is needed because also in the control error, we look basically one step ahead, and that's the corresponding reference. If we want to look not only one step ahead, but n steps ahead, we basically can extend the whole system by an additional state vector, and this additional state vector corresponds to the future references for n steps. Since they are only shifted by one time step, their dynamics is super simple, and in the last equation we basically have only zeros, meaning that after n steps, we assume implicitly that the reference doesn't change it. Okay. So we have a further increased system dynamics, not only with the control error and the differential state, but also with this additional state variables corresponding to the previewed references in the reference. Okay, and in this system description, we now see that the augmented state has exactly the components which we use to the cost function. And if we have this, we can apply a traditional standard LQR controller for getting a linear integration. So this is the idea. We, on one hand, put the differential state and differential input in order to get integral action, and we augment the system by additional variables corresponding to a previewed reference. By computing linear LQR controller for this augmented system, we get the state feedback controller, and the state is this augmented state. So the state contains the control error, it contains the differential state, and the previewed reference to treatments. And since we computed the system with delta U as the input, we also get the control law for delta U. And for going from delta U to U, we basically integrate summarize over these deltas and get the final control law, which now has an integral action of the output error. Since the delta basically, if we remove the delta, we get the sum here. So this produces the integral action. Then we have a state feedback action, and we have this third term, which is a predictive element in the controller, which uses the future reference element, or the elements of the future reference. And if you look at a typical example, how the gains evolve here, especially the gains in these predicted elements, you see that for previewing over different lengths into the future, the gain would decrease. So at the beginning it increases, but then it constantly decreases. And here you see that basically after 1 or 1.5 seconds, the gains are very low. So it means that for the system which was computed here, preview over more than 1 or 1.5 seconds will not really affect the dynamics much. And here you see basically we use this also as a design on how far you want to look into the future in your reference. Yeah, and the example which was published by Klatschmitter in 2003 was the application of this preview control approach to the car labor model formulated by discrete third order dynamics, where the input was the jerk of the CMM and the output is the setting. Then by straightforward application of the preview control, you basically get this, you compute this potential rate. This gain, which was shown here, basically was computed on these numbers, these are technique numbers on this application. And yeah, a typical example is shown now here, where we have a reference trajectory for the CN, which jumps basically from the middle of the foot to the left foot, the right foot, left foot, right foot. And this corresponds to a CN trajectory vectors. And if we apply now the LPR preview control, we basically get the controlled output, which very nicely follows this behavior. And the CN, which also follows it very okay, there's a and what I mentioned already before is that this approach was the first approach which we implemented on our bipedal robot when we started to go in this direction of walking controls. It was for us basically a start in this direction because it's a well understood approach for walking control and for testing if our robot really would walk to basically start with implementing process. Okay. And from this approach, what one can say is that first of all the implementation is very efficient because the whole controller computation can be done offline. And the other good thing is that it allows us to add predictive information into the controller. However, on the negative side, we have to say that the ZMP constraints here are not exactly fulfilled. They are considered, but there are no inequalities considered. And inequalities basically would lead us to model predictive control, which Chris Weaver will for sure talk about. And it's also a trajectory-based approach, meaning that it's usually used in open loop in combination with an underlying stabilizing controller, which has the job of doing the feedback stabilization. There is another extension which is mentioned here, the so-called dynamics filter. I'll come to this in a moment. So what I mentioned about the underlying stabilizer is something, so this pattern generator, which is right here, gives us the desired reference for the CN and the ZMP, and it can be combined exactly with the stabilizer, balancer, so-called dynamic filter. What we discussed here was all computed based on a very simplified dynamics, on the linear the car table form. And in order to make this system fit better to a real robot, what many people do is that they don't only use such a preview controller, but they also compute basically the error the system would produce on the full multibody dynamics. So by using the output of the preview controller and computing the full multibody dynamics, one can get, let's say, a real ZMP one would expect from multibody dynamics. And this ZMP one can take as basically as an offset term in the computation of the controller. That way, the control performance can be improved also quite a lot because it's kind of iteratively takes into account the errors coming from the simplified model solution. Okay, so far I've discussed the, I would say, rather classical walking pattern generator, which was already published 10 years now ago, and which I think is used by many groups as a first approach to start implementing the walking control. Now, in the end of the talk, I would like to come to the approach which we use in our lab. It has a bit of different focus because it basically goes away from pattern generation in general. We don't want to use a pattern generator which works in open loop with the feedback stabilization. Instead, we want to compute the walking controller which does the feedback stabilization already at the same time. So this is our approach. And in our approach, we basically utilize the capture point as the control variable. So for this, we start now with the linear inverted pendulum model, which is this simple linear dynamics. And we know that the capture point is given as the sum of the position and the velocity coordinate. And if we use this coordinate transformation from the CUM and CUM velocity to the CUM and the capture point, then we get the decoupled dynamics, where we have the stable dynamics for the CUM and the unstable dynamics for the capture point. And the idea is then to only stabilize the unstable part of the dynamics. If we do this, if we use this as a control system, you can directly see that we now consider the ZMP as the control input. While in the previous approach, the ZMP was considered as the output. So this is considered as the control input. Okay, so we only stabilize the unstable part of the dynamics. And let's see now how we can utilize the capture point in addition for how the dynamics relates to the trajectory change. And the situation here shows the current state where the CUM and CUM velocity are given by this point in this vector. What we know from the definition of the capture point is that the capture point will always be the line from the current CUM towards the CUM velocity. It will always be somewhere on this straight dashed line. We also know from the second equation, from basically this equation, that the velocity of the capture point is always pointing from the current capture point, always in line between the capture point and the second peak. And that is shown basically if we know that the capture point is somewhere on the dashed line, and we would say, okay, we set our ZMP at this point, then if the capture point is currently here, the capture point velocity would point from this ZMP into that direction. And what we also know is that even if we only consider here the control of the capture point, the CUM will somewhat follow stably the trajectory of the capture point. And from these ideas, you see that the planning utilizing the capture point now simplifies quite dramatically. Because instead of planning a trajectory for the CUM, we basically plan a trajectory for the capture point, and this capture point trajectory always evolves along lines between which, let's say, pointed from the 7B along lines to the next footprint. And in that way, the whole planning basically reduces to a connection of simple lines. Okay, the control approach then is structured as follows. We have a trajectory generator, which gives us basically these lines and the timed capture point trajectory along the lines, which is a desired trajectory for the capture point. Then we have a feedback controller giving us a second P output, and the second P is further projected onto the support polygon, and then has to be implemented by an underlying second P controller. This underlying second P controller is not to be misunderstood as a stabilizer, as a balancer. It's just the controller which implements the second P. It can be a force-based or a position-based controller. What is more interesting at this point is, first of all, the projection of this second P to the support polygon. And here one can see this is the current support polygon, and this is the current capture point. Since the way how the capture point evolves always follows a line from the setting P towards the capture point, you can see basically that this whole support polygon, wherever we place the setting P in the support polygon, maps via this point projection at the capture point into a final footstep for the capture point. And that way we see that even if we have a desired setting P which would lie outside of the support polygon, if we just do a simple Euclidean projection, the final capture point after the step will also be projected. In that way we see that for this projection, a simple Euclidean projection actually is kind of the best of everything. But it's not strictly necessary to handle this control and the projection here so separately. We also tried to implemented a controller which combined the two components. So a model predictive controller which utilized the capture point dynamics and had the second P projection in form of inequalities included in the feedback. Okay, the missing element is basically this underlying second P controller. And for this underlying second P controller, what we want to do is to realize the desired second P via the dynamics of the system. And I said, one can basically use a force-based second P controller, but one can also implement again a position-based second P controller. Since most robots nowadays are position-based, I will present here a position-based second P controller, which basically works as follows. So if we consider a simple inverted pendulum-like dynamics, then a desired second P at this point can be reinterpreted as the desired force acting onto the center of mass. And by this intuitive mapping between second P and the desired force, we can basically go to the same way back. We consider what would happen to a simple classical force controller like this integral force controller, and we get the same integral action for a second P based controller. Just the gain also switches. Okay, so this is one simple version of how to implement a second P controller underlying the controller. And this video you now see some typical behaviors where the robot executes predefined steps here based on the capture point controller is underlying second P. Now in this video, it's basically a set of predefined step trajectories, while here you see more reactive excitation. It's a vision-based working approach. Where we use some vision algorithms, SLAM algorithms from our vision colleagues in order to get a map of the environment, an obstacle map of the environment, and then a colleague from IIT, Nicolas Perrin, who had in research visit implemented an online footstep planning based on this obstacle. And this online footstep placement utilizes information from the stereo processing, so that the obstacle is detected. Basically, it starts to plan always the footsteps. So the system here always copes with reactive footstep. So it's not based on the redefined footsteps. Another application which is very interesting to see is an optimization of the swing foot trajectories. I didn't talk much about the swing foot trajectories so far. I just assumed that they are somehow connected to the moment. And here we had a visitor from University of Tokyo, in Nagoya, who implemented an optimization of the footstep trajectories in order to achieve a bit wider footsteps. Because in our robot, actually, the limiting factor in achieving higher speed is the maximum velocity of the tree. So we have the limit of 2 rad per second, which is okay for normal walking, but also for push recovery, but it's certainly limited in maximum speed. And he implemented basically more optimized footstep trajectory, which allowed to achieve higher walking speeds. And this also was applied to a situation where now the orientation of the body was utilized by the optimization, and then basically the footsteps can be made a bit more wider. However, what is not included here in this system, since there is no upper body in the system, if we utilize the upper body for reaching larger footsteps, what we don't have anymore is angular momentum conservation. So the system may become very simple. With a total upper body, it would of course be possible to do a counter react in order to limit picture. Okay, so this was a set of 2 examples. Here we utilized a structure point-based open controller. And in contrast to what was shown before, it's really a feedback controller which doesn't rely on an underlying stabilizer. So the capture point controller does the stabilization itself. And that brings me now to the summary of the talk. So I basically started with comparing different types of models. Full body models with simplified models, which had an influence on different types of balancers. So while the full body model was utilized for torque-based balancing, the simplified models were utilized either in CNP-based balancing and then in the pattern generator-based balancing. And a similar simplified model was used for this feedback. Okay, so with this short summary of what was presented in the talk, I would like to conclude. Thank you very much for your attention.
I'd like to ask a question. You have the balancing models for standing. How about standing and Bonn? Like, have you created some models for this?
It's basically just the same models for that. Now there's a truck version. What becomes more relevant is to combine angular momentum control with this force-based.
Because it would be very interesting with kicking things, or like, yeah, I mean, just stand on, like, and you kick the ball. So
I think kicking is very much about angular momentum. I didn't talk about angular momentum control. I focused more on force distribution, but for kicking, I think angular momentum control is
Is there a way to combine your trajectories with the Latin orientation so that you can also give a pointing orientation of the footstep? So that you can make the robot look into a specific direction.
yeah, I don't think why you think it would be limited in this book. Because, I mean, when you generate footsteps, you are free to decide the footstep orientation. At the same time, you are free to decide the orientation of the human body. Actually, the orientation of the foot is always different in our case. So one day it came from the land, or completely from the case from the footstep. The algorithm doesn't modify. Actually, I'm not so sure how much the limitation is. Actually, I also don't know where the orientation of the footstep is utilized in combination with the stabilized image. But basically, this is what for this reality is in fact free.
So you use mainly the capture point for getting a reference motion that will stabilize the base of your floating base dynamics. Would it be possible, the motion of the center of mass, so you won't fall over your leg?
But this is not, I mean, the capture point trajectory is computed in order to fit with some nominal foot trajectory. The fact that the foot doesn't tip over is then handled by the feedback controller.
That was exactly my question. So is it possible to relax this flat foot constraint so that you could walk on a line contact, for example?
Yeah, I mean, so our algorithm works on this also as an adaptive footstep placement. If you relax it completely, I think from so that you only have the points, then you don't have a feedback action anymore, which implements this angle strategy. Right? So for the trajectory generation, of course, you can generate an open loop stable trajectory with only foot steps. But then you have to think about how to do the feedback stabilization all over, because I mean this approach utilizes the fact that you can move the ZMP in the foot, that you don't have this point, right? This is the effect of the, let's say, angle strategy. If you reduce this footprint to a point, of course the trajectory is the nominal trajectory, is a nominally stable trajectory, but if you have any disturbance, you have to react. And if you cannot react by moving the ZMP away, then you have to react differently, either by angular momentum control or by adapting the footsteps.
Yeah, so and just like you said, so by adapting the footsteps. So if you say, okay, I don't have a local controller, I just say, okay, I have a disturbance and I compensate it with my next touchdown position. So that would be possible in principle.
Yeah. So we have a recent IROS paper where footstep adaptation is included, but then the focus was more on 3D capture points, so not only walking on the plane, but on different heights. And there, included in the paper is also the footstep adaptation. However, for the footstep adaptation, as far as I remember, there was an analysis. I mean, it worked for the simulations, but the strong analysis which you have for the angle strategy, I don't have it yet for the footstep adaptation. But heuristically, I think yes.
I also have a different question. So the maximal step length you said was 35 centimeters?
Actually, it was with the previous hip, because on this, you see, this hip I don't know the new version was because we changed also the motors in the hip, so I don't know if it's still correct. But with the old, with the iPad only, it was 35 centimeters. On one hand, the hip is redesigned because when we made larger footsteps, you have basically two singularities to go. One is the stretched knee, and the other singularity comes when the first link and the second link are in line, because then the first and third axis are basically over. So for this kinematics, we have a second singularity, which was also limiting the length of the foot. Basically, this was the main limiting factor for the length of the footstep. While here we should be able to make larger footsteps, but we didn't go in this direction. So so far not the robot so long. That time, exchange researcher from Japan worked on his large footsteps using these robots. But I think we should be able to do it. Also, some joints became a bit faster. In principle, it should be possible to make larger footsteps. Even the robot became more familiar.
You show dummy video of the total new robot with leaning to something. So there are contact points in hands. So the situation different in the two legs contact or one leg.
Yeah, actually we didn't use the same balancing controller for this video. So the video is a kind of preliminary experiment. It was one of the first experiments we did with this robot. And there is a compliance controller for the arms in order to limit the force. But I think in principle you can use the same balancing controller by adding more contact points on the arms and distribute the forces. But that alone is maybe not enough, because you should also think about how to weight the distribution such that the robot keeps the main load on the legs and on the little on the arms. Otherwise the optimization might say I try to put all the load on the arms and all the little on the legs. So that is something you have to control by, so far I would say, tuning factors, but maybe there is a more elegant formulation which doesn't have such tuning factors. But I think the principle approach should be the hands of the robot are prosthetic hands, so they are not so fragile, they are made in order to make just enough. And you can also exert some forces on the body.
How do you decide the foot size? As you mentioned that there's a laser for deciding something.
Yeah. Actually, I cannot say we computed some optimization at the foot size cannot. So we wanted to have a smaller foot in order to allow us studying dynamic walking, because you have it outside of the support corridor. Most of it. Then what we also reduced the length of the foot from this version to this version. We reduced the length of the foot in order to be able to step on stairs. So that the foot can nicely step on the stair and not beyond the half. Unless you make very long steps.
Yeah, the small foot that's more dynamic. Yes. If we make big foot, it's going to be more stable.
It's certainly more stable. The foot also becomes more heavy.
Yeah.
But I have to say it's also more steady.
Yeah.
And since the robot is an experimental system where we want to study about walking, I thought we make it big enough so that we can walk stably and do experiments, but not too big, basically. Because otherwise, always research in dynamic walking would be, I would say, confused. Now it's more static walking with more information. And here we wanted to focus on.
Also, I have one question. You mentioned that 3D picture system and CP point pictures trajectory, and then which one is different between 3D picture system and CP point picture system? So what is different to make the trajectory?
Well, the design trajectory is, well, if you have the same set and P, the resulting trajectory must be the same because it governs the same dynamics. Right? But the difference is that if you look at the second order dynamics, you have to plan the second order dynamics. While if you look on a structure point, you have to plan only those lines, which is much simpler. But yeah, so this is about the trajectory generation. The other difference is in the control approach. One utilizes an underlying stabilizer, which is the job of doing the feedback stabilization. While the capture point approach, the way we formulated it, does the stabilization in the same formulation as the generation of the same.
Yeah, I think it was the video with the capture point-based walking of the new Toro robot with the upper body. I saw that the robot was like counteracting what it was doing with the legs with the upper body. But your model is like a concentrated mass model, so how come the upper body is doing these kind of twists?
I mean, actually, I think the concentrated mass model is not a very good model for our. I think it was also not a very good model for many other robot species. It's, I would say, a pragmatic model. And when we have a fast foot trajectory, there is, of course, an effect on the angular momentum. So in order to limit this effect on the angular momentum, we implemented some kind of counter motion. But it was not optimized or computed in this case. It was just, I would say, tuned by hand in order to limit the effect of the angular momentum. Ideally, I would say one should compute really the angular momentum and then have the whole phase optimized. I think it's rather straightforward actually to optimize such a motion, but in our case we had a simple one-type motion in order to have this effect. Basically, I think it is good to have it because, as I mentioned, the concentrated mass model is maybe not the best model for humanoid robots, especially with capabilities. I mean, it's enough to implement walking. I think we want to go much more towards this multi-body models like we have in the balancer, and combining these control approaches with walking stabilization based on quantities like the capture point. It must not be exactly the same, really a quantity which has the same features as the capture point, also for the multi-body. That's the way how we want to go, the way going away from the really simplified dynamics. But I think it's also good to spend some time on the simplified dynamics to understand fully how it works and also what's the real limitation and not, let's say, playing it from the beginning without having it right. So for us, the simplified concentrated mass model is just a start to understand these ideas of the capture point and how it relates to the dynamics. And we also had an extension of the capture point control to the system where you have the full angular momentum. Was one of us drivers, I don't remember. So there we used additional feedback terms for, let's say, forcing the dynamics back into the simple inverted temporal dynamics. Not neglecting the other terms, but basically compensating for it. That's one approach. If that is the best approach, also. So, but we want to go away from this conceptual.
Do you see any limit, like how far you can push the analysis of the dynamics? Because it seems to me that eventually it just becomes so complicated that you just can't compute it anymore. The kind of balancing reactions that humans do when they work on a plank or something like that, where you shift out your legs and your upper body moves in the other direction to balance, which to me really are more reflexes that people do. So we're not controlled in that way. And if you trigger somebody, they do the same reaction, even though it may not be appropriate in that particular scenario. So do you see any limit for? I mean, I think the idea is great. You start with a simple model and then you understand that completely, then you add more complexity. But what kind of motion do you think? Is there a limit, or what kind of motions would that limit then entail? What kind of motion would we not be able to model accurately?
actually from the modeling point of view, so modeling all kinds of motion should be possible. I don't see a clear limit there because you use full multi-body models. Of course, you can add actuator modes to make them more precise, but that affects the overall motion dynamics. I don't see a clear limit there. Where I see a clear limit is if we would try to optimize all the whole body motion.
Okay, yeah.
Then this
So,
is
so
certain.
the optimization.
But you could think about, it's just almost principle, but think like kind of synergies, right? That when you balance on a small area, that you don't move each joint, let's say completely independently, but you have some kind of combined motions how you couple right and left arm in order to do balancing, and then optimize on those simplified, not simplified, but induced variables, which is still coupled to the whole units. That would be one possible way, as I said, makes enough.
Yeah.
From the modeling, I think the limiting factor probably is the prediction. I think for the feedback action, the state feedback action, considering the full dynamics of a 50, 60 degree field model should be possible with a good computer system, maybe but what is much harder is then to include the multi-body effects in the prediction. So I see in that sense a limitation. I think it's just not me, but I think that if we want to do prediction over a longer horizon, we will be limited to models for the prediction, not for all feedback action, but the feedback action might have some predictive part. For that, I guess simplified models will be.
Yeah, I guess we can continue the discussion during the coffee break. So thank you again.